Hi, it's time for another math easy solution. Turn to discuss further into differential equations and look further at population growth, and now go over example 2 of that population growth video series and go over this example, which is pretty much an extension of my earlier example 1 video. Basically, this one states, use the data in the table below to model the population of the world in the second half of the 20th century. So here's a table. And it says, use the model to estimate the population in 1993 and to predict the population in the year 2010. And again, basically I want to note this is the same table as in example 1. So we're asked for the second half of the 20th century. And 20th century is from 1900 to 2000. So we want the second half, split this in two. So from here onwards, from 1950 to 2000, so basically model the second half of it. And just to recap on this, the population of the world was about 1.6 billion. This is in millions, or 1,650 million people in 1900. Otherwise, yeah, or in other words, 1.6 billion, and then in 2000 it's about 6 billion then, and we'll get to 2010 in a bit as we get through this example. Yes, so again, we're going to model from 1950 downwards, and my last video, example 1, was modeling the whole thing out, and it wasn't that accurate for later years. That's why we're doing it for the second half separately. So what we'll do now is basically let t equals to 0. Yeah, let's say let this t equals 0 be the year 1950, just to make it easier to work out the model. So in other words, we're going to start here. Instead of writing t as 1950 all the way to 2000, we'll just set it up like this. So we'll go, this is the time here, time is 0, then this is going to be 10 years. So these are the years after 1950s: 10, 20, 30, 40, 50, etc. This is just easier to work with. So now what you have to do is, well, first recall the population growth model, the differential equation. So dp over dt, or the growth rate of the population, is proportional to the population size, so k times p, where k is a relative growth rate. And also we know that, well, p of 0 equals to po, then this is just the initial population at time is 0. Then the solution of this differential equation is p of t equals to p0 ekt. So again, make sure to watch my earlier videos to get a better idea of this and the proof for it. So that's what we have, but in our initial case, we're given that, well, we're setting up t is 0 to be the year 1950, so then p of 0, that's just this right here. So that's just 2560, so 2560, so then the model is going to be 2560 times it by ekt. So that is our initial model. And now we just need to, well, estimate k, which is the relative growth rate. Let's put the arrow here. So one way of doing that is, let's just pick the next point, 1960. So I'll write use 1960 data to estimate k. So we could just pick this one to estimate k. So when we have that, basically 1960 is the same thing as writing p of 10, because 10 years after 1950 is 1960, and now we're plugging in this 3,040 or 3,040 million people. That's what this value is. And now if we plug it into this model, we have 256 times e, and then k 10. Yeah, because that's the years after 1950, so, or 1960, that's just 10. So now we can estimate k by solving for it. So we'll divide basically this side, both sides, by 2560. So what we end up getting is e, let's write it here, e k, put the 10 in front. Let's write it neater. Put the 10 in front, equals 2 So we're having 340 over 2560. So that's what this equals to, and now we could use the ln property or natural log property to ln both sides so we can cancel this e right there. Yes, so now, and also ln both sides, so we have this, and then the 10k comes down, we have 10k equals 2 ln 3040 over 2560, and also this is divide both sides by 10, just to save time, let's erase that. So we have this 1 over 10, so the 10 goes here, and now we can circle this, that's our k value. And here I've plugged this into the calculator, so just using the Google calculator, 1 over 10 times ln 340 divided by, 3040 divided by 2560, we get this value about 0.017185, and it keeps going on and on. We'll just stop at the 5. So this is roughly equal to 0.017185, and again, recall that the units are per year. Recall from earlier videos that that's per year, and you could also see that when you have a e to the power of something, it's usually, it has to be unitless, so then the k needs to be opposite of the year, so k times 10 years, then divide by the year out like that, so that the time for the years cancel. So you have this kt. T is in years, this one is in 1 over years, so they cancel. Just an easy way of remembering. So what this means again is, this is the relative growth rate. Again, recall my earlier video on the proportionality constant k and how it is the relative growth rate. And this is, in our case, this is about, if you round this up to 1.7 and also times by 100 to get to a percentage, so move decimal place twice, so we get roughly 1.7%, just round down, per year. So what this is saying is that the population grows 1.7% relative to the size of the population per year. So that's what our estimate is. And now if we put this all together, we have our model. P of t is equal to, well, 2560, and then that's our initial PO, times it by E. K now is our 0.017185 t, like that, and that is our model. And now let's now we have the model, let's go back to this, and it says use the model to estimate population 1993 and the year 2000. So let's look at the year 1993. So estimate of 1993. So when we have that, this is 1993 is just, well, 43 years after after 1950. In other words, yes, this is the same thing as writing P of 43, because again, 1950 plus 43 is 93. So that's year 1993. So we just plug this in, 2560 e to the 0.017185, then 43 times by 43 above there. And here, if you plug this into the calculator here, then the Google calculator, so 2560 times e to the power of, there's our k, 0.017185 times by 43, and we get about 5,300, and round this up to 60. I'll just round that up. 5359.9999907, blah blah blah. We'll round it up to the 60. So this is about 5,360 million people. So this is roughly 5360 million. So this is in millions. Yeah, so that's roughly our answer. But we could also write this in billions. Just it's easier sometimes. So 5.36 billion people. So that's how much billion people, that's our estimate from this 1993. But now let's see, what is the exact figure? Yeah, so here again on the Google search calculator, well, if you just search world population 1993 or world population, you're going to get a graph. So there's actually a graph of it. So let's go to 1993. And this sources include World Bank, etc., and other stuff. So we'll just assume this is right. So 5.532 billion is the actual world population in 1993. So we'll write that down. Or here I've just copied and pasted that table right here up to 1993 right here. 1993, and that is basically, this is our actual population versus the estimate right here. And as you can see, it's fairly close. It's off by just under 200 million, which sounds like a lot, but well, compared to when you're speaking about billions, it's not that much. So it's fairly accurate, I would say. Yeah, so now let's look at our 2010 estimate. So estimate of 2010. And again, this is 60 years after 1950, so this is the same thing as writing P of 60. And this equals 2, again 2560 e to the point, see if I remember, 17185, I think that's what it is. Yeah, 17185, and now we times by 60 instead of the 43 as before. So let's type this in again in our calculator. Yeah, so here's our original calculation. Let's just divide this or subtract it, times by 60, and we get about 7178.62, etc. Or I'll just round this up to 7179 million people. So 7179 million. So that's how many million people were. The population. This is our estimate of 2010. And again, this is the same thing as writing let's go 7.179 billion. So about just over 7 billion. So now let's see what the actual population was back then. Yeah, so let's go to that graph again here. Let's just move this over to 2010. As you can see, 2010's is, why is it moving it? Okay, I'll just stop here. So 6.884 billion people. Okay. Yeah, and here I've copied and pasted that answer. So we have, this is 6.884 billion. Now let's write, this is the actual population of 2010. Population. Yeah, so it's off by over 200 million again, but it's still somewhat close. This is 6.8 billion. This is around 2 billion. Yeah, so it's about 300 million-ish off of their answer, but it's still somewhat accurate, because again, we're talking about billions of people, so being a few million off, a few hundred million, it's not that much off. Yeah, so now what I've done is basically made an Excel file. Let's go to it right here. Actually, this was, we'll just change the name of this. This is example 2. I'm basically using this, I just extended the table from example 1. The model 1 and 2, these ones were from my earlier video, so make sure to watch that. And I just extended this all the way from 1900 to 2010 right here. This is our model, the one we just found, 5360 and 7179. Let's just double check. That's what, 7179 and 5360. Yeah, so that's what we had. So these are the ones we modeled, and this is our this is 1950, but I also extended it going backwards, and as you can see, so years since 1900, but I just minused 50 to get the years since 1950. Okay, yeah, let's just go back to that again. So what we have now is, so this is the table of it, and now I have the graph right here. I graphed all 3 of the models. The one for in this video that we just did was, well, this blue one is model 3. That's the one we modeled. And as you can see, it's really accurate past 1950. So I'll just draw this arrow down. So this is past. This is what we did over here. And as you can see, this square one's 2010. This is 2010. This is 1993. The square, and then this is the actual data. As you can see, it's not that accurate going on the left side. but it's way more accurate than these other two models that I went over in my last video. So let's go back to here. Yeah, here, so I've copied and pasted those, basically the table and the chart right here, just to be part of this worksheet that I'm working on. So again, past 1950 is what we did, and here it's very accurate. So past 1950 years since 2000, and 50 years since 1950, since 50. This is the one we just modeled right now. And as you can see, this is very accurate right here. So I'll just write, this graph is, well, pretty accurate. Pretty accurate. Yeah, past 1950. But as you can see, if you were to extend it backwards, this is not that accurate over here. So not accurate. Because you're going to be off from here. This is over 500. This is over $500 million off the actual numbers. But then on the right side for these ones, so again, these ones are not that accurate on the second half of the century. So not accurate right here. Not accurate in later years. So basically, the best way to model this kind of chart is by parts. Basically, model the first half of the century as I did in my earlier video by this green line. This was model 2, or yeah, and then the second half you can model with this more accurate version that I went over, model 3 right here. And again, just for completeness, this is 2010. This is 1993. And again, so I'll write that right here. So thus, better to model, all right, first and second half of 20th century separately. And yeah, let's put that in, underline that. So yeah, that's all for today. And basically, I just wanted to illustrate how to model the population one. But again, depends on which parts or how you break it down. You're gonna have different accuracies, and also when you try to extend for a long period of time, the model, yes, sometimes just goes off because the relative growth rate will change based on the time period. So you can't always assume it's going to be growing at the same rate always. So sometimes it is better to break it up into two. For example, here broke up into two. So this model is better for later years. The earlier models in example 1 are better for the initial years, because those ones will model from initial 1900 as opposed to 1950. So anyways, that's all for today. Hopefully you learned from this pretty extensive example on population growth and world population. And I think the population now should be about, let's just go and check it out, world population. Just type that out, it should give you an answer. So it's about 7.4 billion people as of August 2016. So that's pretty remarkable. And let's see what that actually is right now. If I were to write 2016, 7.9, yeah, so it's a bit off. Yeah, so it's about almost 600 million off. So again, we would better to break it up and make it a new model for later years. So anyways, that is all for today. If you learned, and like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.